All right, today we're going to talk about sigma and pi bonds and shapes of molecules and so forth. And I've been talking about why it's important to the shape of molecules because it determines how those molecules behave, like their shape and what they're actually made of. And these are all painkillers here. And one thing you'll see a commonality in their shape because they have to have a certain shape. People that are trying to develop better painkillers, they know that they have to have this shape to fit into opioid receptor sites. So you see this is a benzene ring, this is a carbon chain here. They have a 3-carbon chain attached to it and a nitrogen in there as well called an amine group. And so they have to have that basic shape. And the only thing you'll see different about these three molecules there is what's attached there to the one side of them. And the heroin got the name because they thought it was the hero drug at the time because it was so good at killing pain. Unfortunately, they didn't realize how addictive it was. And so again, people that are trying to develop better painkillers understand that this is the molecular shape they have to deal with to start with. Your kind of low-level painkillers like ibuprofen, acetaminophen, they work in a different way. These go to opioid receptor sites. Acetaminophen, ibuprofen will actually go to the site of the pain and fight inflammation. Another thing about shapes of molecules and whether or not they're polar or nonpolar, these are vitamins, A, E, K, and D. And the thing is, they're just long carbon chains. And bottom line is, they're basically just carbons and hydrogens. So they're essentially nonpolar molecules, and fats are nonpolar. So if you take megadoses of these vitamins, they will start to build up in your body over time because they'll be stored in your fat, and they can cause negative side effects. So you can't take megadoses of those vitamins because they're nonpolar. But you take these vitamin B6 and vitamin C, because we got these hydrogen bonds here and oxygens on this side. These are polar molecules here, and so they dissolve in water, and so you can flush them out of your system when you take them. So it doesn't matter how much in the wintertime, how much vitamin C you take, because it'll just be flushed out of your system if you take a lot of it. So now let's look at what a sigma and pi bond is, and actually explaining these is always pretty difficult, but what I actually need you to do is very, very simple. Here's the thing. Okay, if you remember back from when we did electrons, you can have electrons in s orbitals, p orbitals, and d orbitals, but when we're talking about bonding electrons, they're usually either in an s or a p orbital. And so when you have, like, let's say the electron and 2 hydrogens, so you got a proton here, you got an electron floating around, I'll put a little negative sign there, and here's another hydrogen because it makes H2, and there's the electron floating around. The electrons being shared in these, what happens is these are s orbitals, round-shaped orbitals. They just overlap between the two of them. So you have what's called a bonding orbital where the electrons are just hanging out between the two of them somewhere. They're on a plane between the two, and that's what a sigma bond is. And so sigma bonds lie directly on the bond axis. That's the bond axis between the two. And any single bond is a sigma bond. Because if you get to a larger element, let's say carbon, its first 2 electrons would be in an s orbital, but remember there's only one s orbital that can hold 2 electrons. So the other bonds, in this case, would be overlapping p orbitals. And if you've forgotten, a p orbital is dumbbell shaped. But again, so if you have, let's say this is the nucleus of some element here, and the nucleus of some element here, and there's the electrons and that p orbital, and draw that correct there. There we go. And there's our other p orbital. And the electrons are still overlapping. There's the electrons right there. They're overlapping between the two. So you have overlapping p orbitals, but if that's still just a single bond, that's a sigma bond. So you can have overlapping s or p orbitals, but again, one single bond, if you have a bond there, that's a sigma bond. Now again, the question is then, what is a pi bond? Well, if you already have a sigma bond, if you have 2 electrons being shared, so if you have 2 that are somewhere in here being shared between 2 elements, if you're going to have another bond, like a double or a triple bond, those electrons can't be in the same place. You can only have 2 in this area. So what happens is you have overlapping p orbitals, but instead of them overlapping end to end in the same space, they're overlapping like this. And I need to show, well, I should have drawn them bigger so that they would actually overlap right here and here. But that's what a pi bond is when the electrons are being shared and they're not on the bond axis, they're perpendicular to it or above and below it. And in 3-dimensional space, if you had a double bond that the electrons are being shared above and below that, you could have one out here and on the other side of this one as well. So the bottom line is this. So any single bond is a sigma bond, and the second bond in a double bond is a pi bond, and if you had a triple bond, the second and third bonds in a triple bond are pi bonds. So it's a simple thing to do. So if we're looking at this and I go, how many sigma bonds are there? How many pi bonds are there? Because that's all you ever have to do. And you go 1, 2, 3, 4. Any single bond, like I say, is a sigma bond. And the first bond in either a double or a triple bond is a sigma as well. So this one would have 5 sigma. And again, the second bond in a double bond, with the second and third in a triple bond is a pi bond, and it would have 1 pi bond. That's all you have to be able to do. So again, all single bonds are sigma bonds, and when you're talking about a double bond, the first bond in that is a sigma, and the second one is a pi. A triple, the first bond is a sigma, and the next two are pi bonds. Last thing we're going to do before we wrap it up today is you need to be able to look at these molecules, because the way they draw them on paper, here's an example. They didn't put the 2 electrons in there, they didn't put them here, so there's some things missing there. All right, so if we look at that structure and they go, okay, what are the bond angles there? The problem is they don't always draw them right, because you don't have 3 dimensions to draw these things on paper. And so when you have to determine bond angles, when they're going, okay, what's the bond angle, and there's your central atom there, you can't look at the way it's drawn, because right now it looks like it's 180 and this looks like a linear molecule, but in reality it doesn't look like that, because what you have to always do to determine shapes and bond angles is go, okay, there's our central atom, it's got 2 bonds and 2 unshared pairs, and you'd go back to your notes and find what 2 bonds and 2 unshared pairs is, and that would actually, so that bond angle there, it would be a bent bond angle, and it would actually make an angle of 109.5, because that's what 2 bonds and 2 unshared pairs, that's what the angle would actually be. And again, for this one, there's our central atom there. We have to see, what's attached to it. It's got 1, 2, 3 bonding sites, but it doesn't have any unshared pairs. Go back to your notes. 3 bonding sites, no unshared pairs. Again, this is what I am referring to. That should be in your notes already. 3 and 0 makes trigonal planar. And in this case, they have drawn it correctly, just because it's on a plane, so it looks the same. So that's trigonal planar. And the bond angle is 120 degrees there. And let's see, a lot of these are just redundant here. One of the things, let's look at this one. We'll do the last one here. And we'll do bond angles, and we'll also do sigma and pi bonds on this one as well. And so we'll do those 2. So the first one there, again, if you're looking at it and you're thinking that's the correct way it's drawn, you'd say, oh, it's 90 degrees. But it doesn't look, here's the central atom. And so you got 1, 2, 3 bonding sites, no unshared pairs. And so 3 and 0, again, is trigonal planar. And the bond angle is 120 degrees. And then this one, that is correct the way it's drawn, because carbon has 8 electrons around it. And so for the second one, it is a linear shape there, bond angle 180 degrees, because again, there's our central atom. It's got 2 bonding sites, no unshared pairs of electrons. But if I said sigma and pi, okay, so let's write that down real quick. How many sigma bonds are there? 1, 2, 3, 4, 5, 6. 6 sigma bonds. Pi bonds, remember, only the second bond in a double bond, or the second and third in a triple bond are pi bonds. So there's a pi bond, and 1, 2, 3 pi bonds. And that's it for today.